This is the second lecture on linear harmonic oscillator, the quantum description of it. First, let me recapitulate what we have done in the last class. The time independent Schrodinger equation with the scaling q is equal to alpha x has become this, with the asymptotic form that it goes as q square. Asymptotically the solution goes as q square by e to the power minus q square by 2. So we consider the trial solution to be this, with the requirement that f is finite asymptotically. Then finally we have arrived at the differential equation to be satisfied by f is this. Now we come to the Hermite differential equation. Hermite differential equation in mathematical physics, we have learned that this is d2y dx2 minus twice x dy dx plus gamma y is equal to 0. It is found that any finite value is a regular point of this differential equation. Any finite x is a regular point of Hermite differential equation. So the region of interest is plus minus infinity. So the region of interest is which matches with the amplitude of the harmonic oscillator, because as the energy increases the amplitude increases. So the classical oscillator oscillates between plus minus capital X with capital X increasing quadratically with energy. As by quadratically we mean that E is proportional to x square. So it is the region. So this differential equation actually matches with the requirement of linear harmonic oscillator. Now we recall that any if we try to solve this equation by Frobenius method or power series method about x is equal to 0, we'll end up with infinite series. For any real gamma, the gamma is there, the gamma, both the solution of Hermite differential equation is in the form of infinite series. Which asymptotically varies as x to the power m e to the power plus x square by 2. So its convergence is not guaranteed. So to confirm convergence or assure convergence of solution, we set gamma is equal to 2n, where n belongs to integer including 0. And if n is even, then the even solution is a polynomial of order n. If n happens to be odd, then the odd solution happens to be an polynomial of order n, again n. But one solution, that is, if we choose gamma to be 2n where n is an integer, then one of the solution is obtained in the form of polynomial. So it is a convergent solution, it gives a convergent solution, while the other solution is is still in the form of infinite series and which diverges asymptotically. So the polynomial solution is known as Hermite differential. It is of order n, is known as Hermite polynomial. H and X. One more thing. In writing this differential equation, we say the value of x is 5. We do not assign any unit to the value of x, that is, x is dimensionless. This is x is dimensionless. So whenever we want to use any differential equation or special functions, the independent variable must be converted into dimensionless form. That is the spirit of converting it into the dimensionless form. So we conclude that if we want to have a finite solution of this problem, even in asymptotic region, this part has to be an integer to n. So the quantization of the harmonic oscillator, quantization in the quantum mechanical description of harmonic oscillator comes from the property of Hermite differential equation. This is the boundary condition, because the boundary condition is that f must be finite in asymptotic region. That forces us to choose the polynomial solution of the Hermite differential equation, that is to set q to be this. So the quantization is the quantization of harmonic oscillator problem comes from the property of the Hermite differential equation. For future use, keep in mind this and the scaling parameter this, which will be obviously this one. I will use this formula whenever required. If we want to give a pictorial representation of this quantization, the pictorial representation is this. This is the real axis, 0, 1, 2, 3, 4 onwards. And if we if gamma lies over there, then infinite, both the solution infinite, both solutions are infinite series. If gamma happens to be at this point, then one solution is polynomial, and the other is infinite series. And this happens for two. If gamma is 1, then the odd series is a polynomial. The even series is an infinite one. If gamma n is equal to 2, n is equal to 2, that is gamma. If n is equal to 2, then the even series is a polynomial, and the odd series is equal to an infinite one. So this one. So what we find that for the convergent solution or physically acceptable solution, one must have gamma is equal to lambda minus 1 is equal to an integer 2n. to be finite asymptotically. The knowledge of the Hermite Hermite differential equation suggests that lambda minus 1 is equal to 2n. So we put a lambda n value. So lambda n minus 1 is equal to twice En by h cross omega. Since it is governed by the integer n, we have put a subscript n in the energy level. So this gives you En is equal to n plus half h cross omega as the quantized energy values. First of all, Planck's theory, if we compare this with the Planck's theory, En Planck is equal to nh cross omega. So this part, this half h cross omega is the addition of quantum mechanics to Planck's result. This energy is called E0 is equal to h cross omega by 2 is called the 0 point energy. If we consider the harmonic oscillator in its ground state, then classically it states that we put the particle, if we consider this is the potential energy curve, then it is classically it is over here with velocity 0. So we are specifying the position and momentum of the oscillator in its ground state, in its minimum possible energy state. We define q to be 0, position and momentum to be 0. Here both this is in contrary with uncertainty principle. Uncertainty principle is not being obeyed in this case. So we conclude that no, it's uncertain. If we have to have uncertainty principle holds good, then this result is not valid. So we say that even in the ground state, the particle has a width. So it may oscillate between these two, so that this part of energy is E0. So the particle oscillates between this. If we consider the particle from thermal concepts of thermal physics, the thermodynamics says that the particle temperature can never be 0. So it will have a thermal energy which is half kBT, which provides half mv square. So the particle will have an energy of this much. This is the 0 point energy. We shall show afterwards through exact calculation that the 0 point energy is in accordance with the uncertainty principle, and if we explain the appearance of 0 point energy from this, it is called the energy of statistical fluctuation. So this is the energy of statistical fluctuation. Energy due to statistical factor. So we see that the energy is quantized. Only thing is that when Planck proposed his quantization principle, there were no uncertainty principle. So the contribution of uncertainty principle was not there. In quantum mechanical treatment, we describe the particle via wave packet, in which the uncertainty principle has already been added, because if we consider an wave packet whose if its spatial extent be delta x, Then if we consider, if we take its Fourier transform and the region of K over which the AK remains finite is, if this is be delta K, then for all Fourier transform this property is satisfied, which is nothing but the uncertainty principle. So if we describe the wave packet or the de Broglie wave by wave packet, then uncertainty principle has already been included, and this is the manifestation of the uncertainty principle, that particle energy, even its ground state cannot be zero, it will have some energy h cross omega by 2, which is called the 0 point energy, which is either the, we may call it as the manifestation of uncertainty principle, or due to the energy due to the statistical fluctuations. Now if we go to the energy levels, we see that the energy levels are equispaced. That is, the first energy, the energy levels are like this. This is the 0 level, and this is En, so this is E0, then the corresponding n values are n is equal to 2, n is equal to 1, and n is equal to 0. The gap between this energy level is h cross omega, this is also h cross omega. So to say the energy levels are equispaced. This is a sole characteristic of parabolic potential, which only seen for that is, if we measure the energy levels of a system experimentally, and we found that the energy levels are almost equispaced, as in the case of diatomic molecule, vibrational energy levels of diatomic molecule, then since the energy levels are almost equispaced, to the first approximation we can treat the system as harmonic oscillator, and then we can add up some terms which explains the slight deviation of the energy levels from its equispaced values. So we have completed our discussion on the energy levels of harmonic oscillator. I now come to the wave function. For wave function, we shall use the fact that this is our wave function. Since it is quantized, some n will come. Let me write it, the wave function. For a given n, the wave function phi n q is equal to some constant nn, normalization constant fnq times e to the power minus q square by 2. If we have seen that for the well-weird solution, this Fn must be equal to Hn^, and it is in the dimensionless form. and the corresponding energy levels is En is equal to n plus half h cross omega. Now first thing is that we need to normalize this wave function. Before going to the normalization, let me recall the orthogonality property of Hermite differential equation. Of Hermite polynomial, which is HMQ HMQ e to the power q square dq integrated from minus infinity to plus infinity. They are orthonormal basis function, and this is root pi to the power n factorial to the power minus half delta mn. This is the orthogonality. So if we consider the normalization of wave function, one thing I have forgot to mention, that this wave function is very important in physics and bears a special name. This is Hermite-Weber function. This is known as Weber function. This entire wave function phi. So what we will have? We will have psi n star q psi m q dq integrated from minus infinity to plus infinity. This should be equal to delta mn, because we write this for this part. This is the normalization constant from phi n, and this is normalization constant from this, and then we will have HNQ. Since Hermite polynomial is a real function, so we are not putting star over it. Then HMQ, and there are the weight factors q by 2, which makes it e to the power minus q square integrated from dq. So the result is and from this part we have in the left hand side we have also delta mn. So for if m is equal to n, then we can write n modulus, which the normalization constant is indeterminate to and phase factor. Sorry, this is plus half. Please check, make the correction that this is plus half. So that the normalization constant becomes, let me check at my, so the normalization constant becomes root pi n factorial to the power minus half. So the normalized wave function is given by This is the normalized wave function. We know that a classical oscillator, for a classical oscillator, this oscillator oscillates between plus minus xn. The amplitude of this, so we have for En h cross omega, and this is equal to half m omega square x square, or if we multiply both the sides by 2, we will have 2n plus 1 h cross omega is equal to m omega square x square, or x, it is the, sorry, this should be capital X and corresponding to the state n, so it is xn square. So we write xn square as, you see omega square gets cancelled, so it is m, and divided by m omega by h line. Note that this is alpha square, so it is 2n plus 1 by alpha square. We introduced that q is equal to alpha x, so that if we go to the dimensionless form of amplitude, this is qn is equal to 2n plus 1. So a classical oscillator, this is the amplitude of the classical oscillator in dimensionless form. Amplitude of classical oscillator dimensionless form. So a classical oscillator in a state n then oscillates between plus minus qn. So in the ground state n is equal to 0, the oscillator oscillates between plus minus 1. In the state n is equal to 1, in the first excited states, the oscillator oscillates between plus minus root 3. Now we shall make a comparison between the classical and quantum result for harmonic oscillator. So we first write the in a wave function in its dimensionless form. Now, how to know HNX? Hn of q can be obtained from this relation very easily. So that H0 of q is equal to 1. H1 of q is, if we put n is equal to 1, this is 2q. And if we write the H2, if we want to get H2, then it is 2q minus ddq operating on H1, that is 2q. So this is 4q square minus 2. This is the, and other states can be evaluated. One thing, note that if n is even, the parity of Hn if n is even, the parity of Hn is even, and if n is odd, then the parity is odd. That is, it is even, this is odd. In general, Hn of minus q is equal to minus 1 to the power n Hn q. This is the parity. We look that the potential for this case is half m omega square x square, and the potential remains the same by changing x by minus x. So the solution should have, the solution of the Schrödinger equation should be decoupled into two classes, even parity and odd parity states. Here it is there. So the energy levels are alternately comes from even and odd state, and the ground state is a even parity state. Now we like to draw the wave function. You recall that the ground state wave function phi 0 of q apart from the constant is simply q square by 2. So it dies as Gaussian function. Symmetric. This is symmetric about the origin. And the classical limit is plus minus 1. So this is the classical limit. This is the classical limit. The particle is confined between this. Recall that we have found out that in dimensionless form classical limit is 2n plus 1. For the ground state n is equal to 0. If we plot psi star psi, so this is the wave function psi 0. Psi star psi, this is psi 0 star psi 0. So it shows that there is a possibility that the harmonic oscillator, even in its ground state, will be found outside the classical region, that is in the classically forbidden region. And the classical probability distribution goes as this. This is PC for n is equal to 0, which goes to infinity at the extremities and passes through a minimum value at x is equal to 0. The minimum value is 1 upon pi. So this is the comparison between classical and quantum mechanical system. If we want to find out what is the probability that the particle will be found in its ground state outside the classical limit, so we need to calculate psi 0 star psi 0 dq from minus 1 to plus 1. On explicit calculation, this comes out to be 0.83. That is, there is a chance of 17% of finding the particle outside the classical limit even in its ground state. This is a similar effect we have also seen in tunneling case. Now we come to the phi 1 state. Phi 1 is, apart from constant, is q e to the power minus q square by 2. So the function is an odd function. It is an odd function. So we initially, when q increases, this part is very small, so this part increases linearly, and with the increase of q, this part starts dominating, so the function will be like this. And it will have antisymmetric nature. This is psi 1. Now if we find the probability distribution corresponding to this, it will be like this. This is psi 0 star psi 0, psi 1 star psi 1. And now come to the classical limit. This is plus minus root 3. And classical probability distribution go like this. This is PC. And if we consider the last state, that so first excited state, it is phi 2, whereas you see that this is even. At x is equal to 0, the wave function has, at q is equal to 0, it is negative, and then increases. So the plot of this function will be like this. This is wave function phi 2. The probability distribution will be and the classical limit is plus minus root 5. This is PC. This is the form of the wave function. In any standard textbook, which you will find more wave functions of this category. For n is equal to 3, the wave function will be an odd one, and so on and so forth. So we end our second lecture here. In the next class, we shall consider the transition probability, in which case we will use the recurrence property of Hermite polynomial.